In the last class, we talked about two different kinds of reactions that you can do with insoluble compounds. One of them is a precipitation reaction where you combine the ions to make the solid and the solid comes out of solution. In the other kind, a dissolving equation, you start with the already formed solid and let it dissolve in water. We're going to do more today with the dissolving type of equations because the calculations you can do are very much related to lab work. Last time I told you about soluble salts that we write the dissolving equation for with a one-way arrow because they're always 100% ions under our conditions. But for insoluble salts, you use an equilibrium arrow because if you just put a little pinch in water, it will set up an equilibrium right away. Silver chloride is the example that I gave, and that's the dissolving equation for when it's in equilibrium. Now, because of the fact that that is an equilibrium, we can write a KEQ. And KEQ is like the same rules we had in the previous lecture. It's products over reactants. And because the products are aqueous, we put them in square brackets for molarity. But when you divide by the reactants, it is a solid, and solids don't go into the equilibrium expressions. So the K is just the product of the molarities of those two ions. When chemists are doing a specific problem, oftentimes they'll take off the EQ and put on a subscript that tells you what kind of problem. SP is what this is called, KSP. It stands for solubility product. It's solubility because it has to do with dissolving, and it's a product because it's a multiplication problem. The first thing we need to know how to do is to write the KSP expression for any salt I give you. And this one, I'm going to give you PbCl2. If you look at how I wrote the dissolving equation, I have 1 lead and 2 Cl minuses. I'm going to keep reviewing the solubility rules today. And if you look at why is lead chloride insoluble, even though chloride is supposed to make everything soluble according to Rule 2, lead chloride is one of the exceptions. So when you write that equation, the Cl minus is going to be squared. That's like any equilibrium constant, the coefficient you use as a power. The next problem is calcium phosphate. The reason why I picked that one is because that's all the bigger numbers we ever get in salts, 3 and 2. It never goes higher than that. So I want to also look at why is calcium phosphate insoluble. And that is because of Rule 4. All phosphates except for Rule 1 and ammonium are insoluble. This time when you write the equilibrium, you have to have a 3 in front of the calcium, a 2 in front of the phosphate. So in the KSP expression, calcium is cubed and phosphate is squared. Now you might say, why do we do this? Because KSP expression mathematically is nice, but unless you have values for it, you can't really do any problems. I want to show you that chemists can measure the KSP values of all of the insoluble salts that have been studied. And then we give a table of them so we can look them up in order to do problems. This is the experiment that chemists would do to be able to calculate a KSP. Suppose you wanted to calculate the KSP of silver chromate. That is an insoluble salt. It's reddish brown colored. And when you dissolve it, you want to find out how much dissolves. What chemists will do is usually take a liter of water or 10 liters or whatever, and they'll weigh out a starting amount of silver chromate, maybe 1 gram. And then you stir it mechanically until you're sure everything dissolves. You can filter the solid out and dry it. and weigh it again. Whatever the difference is how much dissolved. So if you put in 1 gram and after dissolving you now have 0.9 grams left, you know that 0.1 gram dissolved. And from the amount that dissolves, you can calculate what the concentration of each ion is in solution. And so in this case, I gave what the concentrations of silver and chromate would be. You can't get more of them to dissolve by adding more of the solid because the solution is already saturated. So these numbers are going to be the same anytime there's solid in equilibrium with them. All you need to do to get the KSP value is to write the expression, which has silver squared in it, and plug in those two numbers. When you do it on your calculator, you're going to get actually not 1.9 times 10 to the minus 12. You're probably going to get something like 1.89 something, and I rounded it off to two significant figures. I know that this is something that a lot of people won't need, but I still want to show it to you because calculator use is so important to getting the correct answers in this class. How do you enter scientific notation? The best way to do it for me on a graphing calculator is to use the key that has an EE. Now that on a TI-83 or 84 is above the comma. So if you hit second comma, it's the EE key. It might be EXP on some other calculators or whatever. But on a TI-84, you would enter 1.56 EE, and a little e comes up on the screen. That means the power of 10 comes next. And so you hit the minus, and there's a key with parentheses around the minus. That's the change the sign key, not subtraction. So then enter minus 4. In order to raise things to a power, you can always use that caret key. There's other keys, maybe x squared, x cubed, whatever, but you can always use caret 2. And then you multiply by the other number. And what should come up on the display is the 1.8977 e minus 12. Sometimes on some calculators, when you hit the exponent key, it actually gives you something like 10 raised to a power, and there's a blinking box as the power. That works also, and you just enter the power in that box. If you look now down below, it says there's an alternate way, and a lot of people like to enter scientific notation this way because it's more intuitive. But there's one caution that you absolutely have to pay attention to. If you enter scientific notation as 1.56 times 10 caret negative 4, you absolutely have to put parentheses around it. If you don't do that, the calculator will square the 10 to the minus 4, but not the 1.56, and you'll get the completely wrong answer. So if you're going to use scientific notation the way I showed it here, please remember to put parentheses around all scientific notation. If you do that, you'll get the same answer. Nobody really uses regular calculators anymore too much, so I want to show you that in your book, Table 1, which covers page 3 to 7, is a table of KSP values. And if you have your book, if you turn to page 3 and look through those pages, you can see that there's a column that has the KSP values for all the different salts. Now, the way I arranged them is that they are by the negative ion in alphabetical order. So bromides are on the first page and they go all the way to the end in page 7. If you look at those numbers that are in the tables, they are very small. They're 10 to the negative power. And there's a reason for that because we are dealing with insoluble salts. So what you're really doing is you're multiplying the concentrations of ions like silver and chromate that come from insoluble salts. There are not going to be many ions because it's not very soluble, and so the numbers are not going to be very big. But if you look at another part of it, the numbers are also not anywhere near equal. You can find KSP values that are anywhere from probably 10 to the minus 6 or 7 all the way up to 10 to the minus 50 or more. That's because everything dissolves to a completely different amount depending on the salt. And I want to show you the difference between how soluble these different salts are. It's unfortunate that we're not going to do the group 4 and 5 experiment in the lab because we're not doing it in class. But if you were doing that experiment, this concept is still the same. If you look up the solubility KSPs for the two salts, barium chromate and strontium chromate, you will see that they differ by 10 to the minus 11, and the other one is 10 to the minus 5. Now, it doesn't maybe look like so much until you examine it. So the first question I want to ask is which of those two numbers is actually the bigger one? I wrote those out to show you that the 10 to minus 11, you have to have 10 zeros before the 8.5, but with the 10 to minus 5, it's only 4 zeros. That means even though 11 looks bigger than 5 when it's a negative exponent, the strontium KSP is actually larger. One of the things you can tell then is that what does it mean that there's a larger number? Well, what we're measuring is how many ions are forming in the solution, which means how much actually dissolves. So you are getting more ions if you have a larger KSP. And if you're forming more ions, the reason is that the salt is more soluble. So you can say that the larger the KSP, the more soluble the salt is. And so strontium chromate is much more soluble than barium chromate. The thing is, what you might not recognize right away is how many times more soluble is it, because people have a hard time with negative powers of 10. If you're dealing with positive powers of 10, people can usually figure that pretty well. If you think about what's about 1 mile away from Moraine Valley, you could probably visualize it. You say, what's 10 miles away, 10 to the first? You could probably visualize it. Maybe your house, maybe stores. What's 100 miles away, 10 squared? Now we're talking about the whole Chicago area practically. What's 1,000 miles away? Now you're up into Canada, probably a third of the country. If you say, what point could you find that's 1 million miles away, or 10 to the 6th, from Moraine Valley? You might feel like you're in outer space if you're in a chemistry class, but in that case, you would literally be in outer space. So people have a feel for positive powers of 10, but for negative powers, a lot of people, when they look at a negative exponent of 10 like that, they just think, oh, that's just 0. It's not that big. It's no biggie. The thing is, it's not true. They differ by just as much as the positive powers. I'm in biochem, and so one of the things I always think about is, for example, how big is a prokaryote? If you think about E. coli, the number that comes to mind is like 1 times 10 to the minus 6 meter. If you ask how big is a eukaryote, like an algae, it's more like 10 to the minus 4, because the exponent is a 10 squared different. That is 100 times bigger. A bacteria is just a tiny little speck compared to an algae. Then if you go down to a virus, you can find viruses that are 10 to the minus 8, 10 to the minus 9. That's the reason why those T4 phages that they show on the surface of E. coli are just like little teeny things. But when they inject DNA, they can kill the whole cell. So the difference between those powers of 10 is very significant, but you have to kind of train yourself to see that if you're in science. I want to ask how many times more soluble is the strontium chromate than the barium chromate. In order to do that, we have to divide the two KSPs. If you take 10 to the minus 5 divided by 10 to the minus 11, this is mathematically what they want you to know. For example, if you're taking the MCAT or the PCAT and they ask you questions, they want you to know some of these powers in your head, how to do them, and some of the simple logs and things. So I want to go over some of these things. The way you do this in math is when you have the same base divided, you subtract the exponents. So you're going to take 10 to the negative 5 minus a negative 11, which is plus 11, and that's going to come out to 10 to the 6th. So these two salts differ in solubility by 10 to the 6th times. And that's actually 1,000,000 times different. We use that in the lab actually to separate barium and strontium, because barium precipitates much more easily because it's so insoluble. 1,000,000 times is a huge difference. Now I just want to throw in one more salt so we can compare them. So on this page I want to throw in silver chloride. If you look that one up in the table, it's 1.8 times 10 to the minus 10. So if I asked you to rank the three salts that we already have looked at in order of most soluble to least soluble, you want the biggest to the smallest, which means you're going to be strontium chromate is the most, barium chromate is the least. That's pretty easy, but in the next salt, if I throw in a fourth one, there's a problem, and I want to show it. If you want to throw the salt in silver chromate that we calculated before, the KSP is 10 to the minus 12. Now, if you were going to put that in the list we made, you would probably want to put it at the very bottom because it's the smallest number. The problem is you can't do that, and I want to show why. There's something mathematically different about the expression for silver chromate than there is for the other three salts. The silver has a square on it, whereas the other ones all had exponents of 1. Because of the square, it throws the mathematical comparison off. You can't compare directly. Now we're going to do a problem all the way in homework 8 where you can calculate whether silver chromate or barium chromate is more soluble, but you can't directly compare them if the exponents aren't identical. I'm not going to trick you with this. If I ask you which of the following is the most soluble, they'll all have the same exponent. This is just so you know about it. Can you write a KSP value for a soluble salt? And you see that the answer is no. If you dissolve sodium chloride in water, there's not going to be any solid left. We never get to saturation with soluble salts. And so if you were going to write a KSP, you can't eliminate the denominator unless there's some solid present. As long as there's solid, you don't have to put it into the equilibrium expression. But if the solid is all gone, you're not even at equilibrium. If you were going to write a KSP for this, you would have to divide by 0 because there's no solid. And of course, you can't divide by 0, so chemists consider that the KSP for soluble salts is undefined. You can get a number for it if you finally saturate it, but the number is so big that they're not really useful for soluble salts. So at the bottom of this page, I summarize what we know so far. The larger the KSP, the more soluble the salt, and there are no KSPs for soluble salts. So that means that all the salts that are listed in your table, table 1, are insoluble. We want to use this stuff to try to do a real lab problem. If you were going to do precipitations in the lab, which is how you separate ions from each other, you have to make sure that a precipitate is going to form. Otherwise, you can't do the experiment because it's not working. If you put together two ions that should form an insoluble compound, you can still be below the solubility level so that they won't precipitate anyway. You have to be sure that you're adding enough of each. And that's where these will it precipitate form problems are coming from. You want to be sure that if you do an experiment in the lab, that you will get a precipitate. And so this question is going to ask, will a precipitate form if you mix a certain amount of silver ions with a different amount of chromate ions? What you're really doing is you're mixing together silver and chromate from two different sources, and after they dilute each other, they have the concentrations that are shown in that picture. The question is, will they form a precipitate? The first thing is that if they are going to form a precipitate, it has to be the one that you get by crossing. You can only make a neutral ionic compound. There are no other compounds between silver and chromate except Ag2CrO4. That's not true of covalent compounds. There can be multiple compounds between different nonmetals because they're sharing electrons, not positive to negative attractions. But when it's ionic, there's only one compound possible, the one that makes it neutral. And as I said, even though silver chromate is insoluble, it doesn't necessarily mean that it'll precipitate unless you get enough ions in the solution to overwhelm the solubility limit. When I ask a question like this, I will usually ask it, will a precipitate of silver chromate form? Now, I do not have to put that in, but the reason I put it in basically is because I am a sweetie pie. I want people to get the question right. What students typically forget to do is to square the silver when they do this problem, and so they get the wrong value. I figure if I write the formula, you can see the 2, and hopefully it'll remind you to square it. The question is, how do you determine whether there will be a precipitate? You just have to hang in there with me for a second, and I will show you the process, and then we'll explain how it came to be the way it is. This is the procedure whenever you have a will it precipitate form problem. You're going to first of all write the dissolving equation for the salt. And you can look up the KSP in table 1. That's the reason we have it. When you go to the table, you can find silver chromate 1.9 times 10 to the minus 12. Now the next step is to write a Q. Please remember what Q is. Those two concentrations that I give you in the problem are being mixed. That means they are not at equilibrium, they are initial. And when you want to plug in initial concentrations instead of equilibrium, you call it Q. I'm then going to plug in the two concentrations and calculate the Q value. I want you to make a connection in your head. Whenever you see the words in a problem, will a precipitate form, I want you to identify the fact that that is a Q problem. Now what we're going to do is compare the Q and the KSP. The Q 10 to the minus 8 is larger. So that means that Q is greater than KSP, and we're going to be able to tell from that which way the reaction has to shift in order to reach equilibrium. Last time I showed you this box at the bottom of 45. This thing keeps coming back all the time in this class, and this one, it comes again. When it says that when Q is greater than KEQ, you shift to the left towards the reactants. So if you do shift to the left, the question is, what's on the left? You're shifting towards silver chromate, which is the solid. If you put in enough ions so that you shift towards the solid, what does it tell you? It tells you that a precipitate, or the solid, is going to form. That's how you know, by comparing Q and K. There will not necessarily be a precipitate just because you mix those two ions. Let's say you clean out the flask and do another problem where you mix different amounts, 10 to the minus 6 silver and 10 to the minus 3 chromate. It's the same mathematically, so you're going to end up with a Q that you plug in those two new numbers for, and then compare that to the KSP. You can see that in this case, the Q is actually less than the KSP. And whenever Q is less than KSP, you shift to the right, away from the solid and towards the ions. What that means is there will not be a precipitate because the solid will not form. The problem that we've done is perfectly okay, where I give you the concentrations of the ions, but it's not totally real in one sense. You cannot have silver ions in solution by themselves. The only thing you can buy from a chemical company are complete ionic compounds that are neutral. If you want to get silver ions into solution, you have to put a negative ion with them that will serve as a spectator, but that you're sure will make silver soluble. What possibilities do we have for negative ions that could do that? I gave you 3 possible negative ions in solubility rule 2 that can make everything soluble. In the case of silver, chloride won't work because silver chloride is one of the exceptions. And I don't want you to know this exception, but silver acetate would not work either because it is insoluble. The only one that will work in this case is going to be silver nitrate. That's what you use if you want to get silver into solution. And the silver nitrate is a very important compound in medicine. They still use it, that when a baby is born, it's very easy to get a fungal infection in the baby's eyes from the birthing process. So after they clean the baby up, they still put drops of silver nitrate diluted in the baby's eyes because it kills fungus, and that way it keeps from getting the infection in the baby's eyes. Now the other ion, chromate, we also have to get into solution by putting a positive ion with it. What would you expect would be a good positive ion? Well, in this case, if you look at solubility rule 1, it says that any salts of alkali metals or ammonium are soluble. So you could pick any of the ions from group 1, and it would make the compound soluble. I'm going to use potassium chromate because when we use chromate in the lab, that's what you use, is potassium chromate. So this one I'm labeling as kind of a real problem. Will a precipitate of silver chromate form if you mix that amount of silver nitrate with a different amount of potassium chromate? So I'm giving you the complete compounds. What you're doing is you're still going to mix silver nitrate and potassium chromate together in 2 beakers. And when you dump them together, the 2 extra ions, potassium and nitrate, are going to be spectators. So it's still the silver and chromate that are going to form the insoluble precipitate. So we're going to do this problem exactly the same way. It's a will a precipitate form, so we're going to write the dissolving equation of the solid, look up the KSP, and write the Q. This time, though, I did not give you directly concentration of silver ion or chromate ion. What I gave you were the compounds. So I gave you the concentrations of silver nitrate and potassium chromate. I can't just automatically plug those in unless I prove that I can do it. And so how are you going to get the actual concentrations of silver and chromate from the concentrations of the compounds? I'm only going to show this process once because it's going to derive a rule that you can use for every problem that's simple. but I want to show you where that comes from. Let's suppose that you were going to dissolve silver nitrate in water, and you started with the concentration I give you in the problem. Question is, how much of each ion would you end up with? In other words, after the silver nitrate dissolves, how much of that AgNO3 units will you have? Well, none, because they split apart. How much of each ion will you have? There are people that swear that since you're splitting it apart into two, you have to get half as much, but that is not the way stoichiometry works. There's a 1 in front of each one. That means that however much silver nitrate you dissolve, you're going to get exactly the same amount of each ion. The only one we're really interested in, of course, is the silver ion. But why are they the same? A lot of people have trouble understanding this, so I tried to draw a picture to show you why. If you took a compound that was made of red and blue circles and dissolved them in water, you're going to split them apart 1 to 1. If you dissolve 10 of the molecules, how many red circles would you get and how many blue ones? Since it's 1 to 1, you're going to get 10 of each. This is how it always works when you divide something 2 to 1, or when you divide one thing into two parts. And we don't really care about the nitrate because it's a spectator. So the truth is we can use the number from the problem to plug in for silver. We now have to determine whether that's also true for potassium chromate. If you dissolve potassium chromate in water, it's true that you are going to get twice as much potassium ion because there's a 2 in front. So when you figure out the amounts of ions, it is going to be twice as much of the potassium. The thing is, the potassium, again, is a spectator. The reason why it's 2 times as much potassium, let's suppose you had K2CrO4 is 2 gold circles and a purple one. If you put 10 of those in solution and let them split apart, you're going to end up with twice as many, or 20 of the gold ones and 10 of the purple one. But since we don't care about the concentration of potassium because it's a spectator, you can use, again, the same concentration of chromate that I gave you for the compound in the problem. In our problems, it's always going to be allowable to do that. The only time when you wouldn't be able to do that is if you had a spectator that did not have a charge of 1, because you would be crossing down something other than a 1 on the opposite ion. But if you think about it, what are the positive spectators? They are the group 1 ions and ammonium. All those are +1. And what are the negative spectators? Chloride, nitrate, and acetate. Those are all -1. And so you could, I would only be able to do this if I could figure out a -2 spectator, and the only one I could really think of was sulfate, that is sometimes a spectator, but sulfate makes things insoluble pretty much a lot of times. So I'm not going to do that. I'm just going to say cross out the spectators and plug in the numbers that I give you in the problem. If we go back to that problem with the complete compounds in it now, we can do it because all you have to do is cross out the spectators. If you were doing this without drawing the pictures, though, how would you know what the spectators are? Well, obviously, the spectators are the ones that are not going to show up in the solid. So in silver chromate, those are the ions we're going to actually end up with. So if you look at silver nitrate, nitrate is going to be the spectator because it's not in the solid. And for potassium chromate, K is going to be the spectator because it's not in the solid. So after you cross those out and plug them in, you're going to end up with a Q value, and in this case, the Q is greater than KSP, so you do get a precipitate. Now, one alternate problem that I want to do from this is one that the American Chemical Society says that we're supposed to do. In general chemistry, we're supposed to do the problem where we can give you any of the 5 types of reactions: decomposition, addition, single and double displacement or combustion. All we're supposed to give you is what reacts. You're supposed to be able to predict which type of reaction will occur. You're supposed to be able to write the products yourself by crossing or by covalent bonding or whatever. Then you're supposed to be able to balance, and if it's in solution, write a net ionic equation. That is a problem that you have all the knowledge you need to do. But in Chem 131, it's a lot. It's just kind of too much for people at the stage of the career where you are. I only want to do it for one type of reaction, and that is double displacements, because both precipitation reactions and acid-base reactions are double displacements, and those are the two that we're going to talk about mainly in the first part of 132. So the way this question is going to be stated would be, if I showed you the 2 reactants that are on the screen here, I would tell you to write the net ionic equation for this precipitation, and it's a double displacement reaction. So how would you do that by steps? The first thing is that when you dissolve those 2 compounds in water, you're going to get ions. So what you're going to do is switch the 2 metals. You put the K with the NO3 and the silver with the chromate, but you do not carry over the subscript. So in other words, you're not going to put a 2 for the potassium, because that's not the way the compounds are going to reform. They are going to reform so that the neutral compounds are the ones that form, and that means you have to cross. So you first switch the ions, and then you get the formulas by crossing. So when you cross the 1s for the KNO3, it stays KNO3. When you cross the 2 down on the silver, you get Ag2CrO4. When you do this crossing, you almost always mess up the balancing. So the next thing you have to do is balance. These are not difficult balancings, though. Usually all you have to do is put in a 2 on each side or a 3 on each side. There's some other ones that come up, but let's look at what you would have to do to balance this. Since you crossed a 2 down on the silver, there's 2 silver now on the right side of the equation. So in order to balance the silver, you would have to put a 2 in front of the silver on the other side. You remember you can't put the number in between the compound because that doesn't mean anything, so you put the 2 in front. But then that created 2 nitrate on the left, and there's also 2 potassium on the left, so you need a 2 in front of the KNO3 on the other side, and we're balanced. That's it. Usually if you add a couple of 2s or a couple of 3s, that will do it. There's some problems where you have to add a 2, 3, and a 6. I put one of those in your homework, but by that time you'll have done some of these, so you'll recognize how to do it when you get there. When you're doing these, you then have to figure out which one is going to be the precipitate of the 2 products. Well, there's 2 different ways really to do that. KNO3 cannot possibly be the precipitate because potassium makes everything soluble, and so does nitrate. So if you put the 2 of them together, they are not going to precipitate. If you wanted to check to make sure that silver chromate was a precipitate, you could look in Table 1. Remember, Table 1 only has insoluble compounds in it, and that would verify that silver chromate is the precipitate or the solid. And remember that you can write those 2 compounds as the products in either order you want. You can put Ag2CrO4 first, There's no rules about that. All it is a list. So you can put the reactants in whatever order you want, and the same for the products, as long as they're on the correct side of the arrow. If you were going to write a net ionic equation for this now, I want you to primarily do it by the shorter method, because in the lab, if we were doing it, this is the quick way, and we want to do things relatively quickly. I also want to show you the full method though, but let's do the quick one first. I'm showing this in step 6 at the bottom. What you want to do is write the net ionic equation for the precipitation. Whenever you're forming a precipitate, you can always do this. You just put the solid on the right of the arrows, because that is what's forming. And then on the other side, you put the two ions that come together to form it. And the two ions are silver and chromate, and the silver has to have a 2 in front in order to balance. So this is the net ionic equation for the precipitation. And in the lab, we usually don't care what the spectators are, or if there's buffers or other things. All we want to write is what actually happens. I did show in the previous class, though, that there's another way to get this. You can split up the compounds and cross out what's the same on both sides. So let's try that. You can split up the silver nitrate into a silver and 2 nitrates, the potassium chromate, 2 Ks and a CrO4, the KNO3, 2 of each of the ions, and you leave the silver chromate together. And you can cross out the K and the NO3, which are the spectators, and you end up with the net ionic equation. For some of the other reaction types, you might have to do this in order to get the net ionic, but for double displacements, it's usually easier, and you don't have to go through that whole thing. You might have asked this question while we were going through this, and a lot of people asked me, so I wanted to deal with it. The question we've been asking is, will a precipitate form? It seems a little weird that the first thing I tell you to do is to write a dissolving equation rather than a precipitation equation. But you could do it either way, but the way we do it is with a dissolving equation, and I showed you there, it's basically because of tradition. Chemists have usually chosen to write the precipitation equilibria as dissolving rather than precipitating. And the truth of it is, you can do this problem either way. If you wrote the dissolving equation backwards so that it was precipitation, as long as you had a K for it, all you want to do is know, are you going to shift towards the solid or the ions? It doesn't matter what side they're on. So you could use either one. But there is a group of people that meet in France that you're going to get to be very familiar with in organic. They're called the IUPAC, the International Union of Pure and Applied Crackpots. I mean chemists. I'm sorry, I made a mistake there. They meet in France. They come from all over the world. They're chemists from all over the world. And they make the rules for chemistry. If everybody used a different language to communicate chemical results, and you write it all differently depending on what country you're from, we wouldn't be able to communicate. So this group agrees on how to write things scientifically so different nations can, the scientists can communicate with each other. They have decided that we are going to write dissolving equations only, and that's all you'll find in tables. And so that's why we do it. You're going to get very familiar with the IUPAC if you take organic chemistry, because they're the ones who came up with the naming rules for organic compounds, and the organic chemistry teachers have told me that about a third of the organic class is just plain naming, because everybody has to learn this system of how to name organic compounds. If you look at the heading of this problem, I consider myself to be pretty famous for these. I'm going to call it a grand example problem. A lot of times in classes, I will try to come up with a problem where we do everything we did that day in one problem. And this is my attempt at it for this class. So I want to ask, will a precipitate of aluminum hydroxide form if you mix that concentration of aluminum? What is that? Are you getting familiar with it? C2H3O2, that's acetate. It makes everything soluble, one of our main ions. If you mix aluminum acetate with that amount, 10 to minus 5 molar sodium hydroxide. So that's the question. Because it's a will a precipitate form problem, you can say this is a Q problem. And in order to get Q, you write the dissolving equation for the solid and the Q expression. So you're going to cube the OH. That is by far the most common thing people forget to do. They just take the numbers from the problem and multiply them, but that does not work. If there's a 3 in front, you have to cube it. And the KSP just comes straight from table 1. Aluminum hydroxide is on page 5 in the table because that's where the alphabetical order for hydroxide is. So now we have to get values for aluminum and hydroxide so we can plug them in and compare it to the KSP. You get the values for those by crossing out the spectators, just like we showed. If you look at which ones are the spectators, the spectator in aluminum acetate is going to be acetate because aluminum is in the precipitate, and the spectator for sodium hydroxide is going to be sodium because hydroxide is the one that's in the precipitate. So if you just cross out those two spectators and use the numbers directly from the problem, you plug them in, cube the OH, and you find out that Q is greater than KSP, so a precipitate forms. Next, we're going to do the complete imbalance equation. Let's suppose that you were not told which of the compounds that form is actually the precipitate, and you have to figure it out for yourself. You would then get this kind of a problem. If you mix together aluminum acetate and sodium hydroxide, it's a double displacement or metathesis reaction. I want you to write the net ionic equation for the precipitation. The first step is that you switch the metals. So you put the sodium with acetate, the aluminum with hydroxide, and you could put either one of the final compounds first, it doesn't matter. But after you switch the metal ions, you then cross. When you cross, you get sodium acetate with 1s, of course, because they're both 1. But for aluminum hydroxide, you cross the 3 down and you get AlOH3. The next thing you have to do is balance. I always suggest look at what you crossed, because you crossed a 3 down on the OH, so you're going to have to get 3OH on the other side. So first I put a 3 in front of the NaOH to balance the OH. That gives me 3 sodium, so I need to put a 3 in front of the sodium acetate on the other side, and it is balanced. If you count each of the ions, they're the same number on both sides. If you did not know which of the two compounds that formed was the solid, you could do it actually 3 different ways this time. Sodium acetate cannot be insoluble. It can't make a precipitate because both of those are soluble ions. AlOH3 is in table 1, which means it's insoluble, but AlOH3 also has a solubility rule. This is the only one I haven't reviewed yet, so let's look at it. Solubility rule 3 says that metal hydroxides are insoluble, and aluminum hydroxide is one of them. The only ones that are soluble are the ones that have metals from group 1 and strontium hydroxide and barium hydroxide. You can then for sure put the solid after the aluminum hydroxide, And the next step is you want to write the net ionic equation. Since you know what the solid is, all you have to do to get the net ionic is to put the solid on the right of the arrows, and you put the ions that make it up on the left, and there has to be a 3 in front of the OH in order to balance. It is possible to do this by splitting. I don't want to go over that in detail, but I am going to show you that it does work, and you're going to end up crossing out the spectators and getting the correct net ionic. So at the top of the page here, I show that you do get the net ionic equation if you split apart and cross out the sodium and the acetate. Now, the whole first half of class is really summarized by that picture at the bottom of the page. If you can take this picture and understand what we did, you will be able to put in numbers, and that's going to explain everything we did. What you're doing is you're always going to take two soluble compounds, mix them in the same beaker, and two of the ions are going to be able to combine, but the other two aren't. The other two are spectators, and that's where you're going to get a precipitation reaction. Now, if you wanted to turn this into what we're going to talk about next, you want to turn it into an acid-base reaction. Why is that a double displacement? All you would have to do was, instead of using Al3+, you could put in H+ as the positive ion. The H+, of course, comes from an acid, and if you use that instead of a metal ion, you're not going to form a precipitate, but H++ OH is going to form water. The thing is, water is unionized, and therefore it's going to stay together even though it's not going to fall out of the solution like a precipitate would. So acid-base reactions also are double displacements, and the two spectator ions then are the ones that would be present in the salt. In this second part of the class then, we're going to cover a topic that doesn't look like it's really that related, but it's important to both of to all of the things that we're going to do from now on. So I wanted to cover both of those things today so we're ready in the future. I want to talk about how chemists measure the acidity of a solution. And I showed the classic example of HCl, which is stomach acid, hydrochloric acid. If you looked up in a table the electronegativity values of H and Cl, please remember what electronegativity is. The larger the electronegativity, the greater the ability of the atom is to attract electrons. Since chlorine has a larger electronegativity than hydrogen, the electrons in that covalent bond between H and Cl are already slanted towards the chlorine. This is what's called a polar molecule because you would get a partial negative charge on the chlorine and a partial positive charge on the hydrogen. The thing is, it is still covalent when HCl is in the gas phase. But when you put it in water, the water acts just like a knife and cuts the H+ off, and it completes the transfer of the electron to the chlorine. And then chlorine has 8 electrons, which you know is an octet, and it gained an electron, so it's negative. The hydrogen has lost an electron. They call it a hydrogen ion, or sometimes they call it a proton, because what is a hydrogen atom? It's actually just a proton with an electron around it, and if the electron is gone, all you're left with is a proton. Water has a tendency to do this. It separates charges, and you can show in physical chemistry the reason it does that is because water is hydrogen bonded. The H from one of the water molecules is almost positive because the electrons are being pulled by the water so much, by the O so much. So the hydrogen kind of forms a partial bond with the next oxygen over, and that's called a hydrogen bond. Anytime hydrogen is attached to either an oxygen or a nitrogen, it can form hydrogen bonds. And water has what's called a high dielectric constant, which in physics means that if you put something between two charges, it will partially block the charges from each other. The larger the dielectric constant, the more it blocks the charges. Water has a very high dielectric constant, and so it tends to separate charges, and in acids it does that. It tends to split the H plus away from whatever it's connected to. H plus cannot exist all by itself in water. That's a proton. If you're talking about protons, you're talking about nuclear chemistry, and we're not going to talk about that yet until way later in the course. What H plus does, when you put it in water, is that it actually combines with an H2O molecule. One of the two unshared pairs on the oxygen actually can form a bond with the H plus. And once that bond is formed, you cannot tell the difference between the three bonds, and the positive gets smeared out over the whole polyatomic ion. The kind of a bond it forms between the oxygen and that H plus is called a coordinate covalent bond, or a dative bond, which is a bond in which both of the electrons come from the same atom. Hopefully you heard about those a little bit, at least in 131. They're very common in organic and also in inorganic in ions. So what you end up with is the ion that's called hydronium ion, H3O plus. This is what it actually means when you see H plus aqueous written. I'm not going to write it as H3O plus, because if you do that, then whenever you're balancing, you have to write that extra water in. And so writing it as H plus aqueous is much easier. Sometimes you have to remember that the H plus is attached to a water molecule as H3O plus. If you have to remember that, I will remind you, but usually you can get away with writing it as H plus aqueous. The thing is, the reason why the H plus is what reacts is that water is just a carrier. Water molecules pick up the H plus and carry them around. So they can either grab the H plus and make H3O plus, or they can lose the H plus to another substance. And so water is really just a carrier. It's actually the H plus that's reacting. And here I just want to emphasize that since the H plus is being carried by a water molecule, it's not ever actually free in solution, but we write it as H plus aqueous anyway to show that that's what reacts. As far as OH, there's not much to say. Bases are the ones that produce OH, but OH doesn't really react with water. All that happens is water surrounds it in a hydration shell that's aqueous, but OH is pretty much what it is, OH minus. We're going to try to show where the pH scale comes from, and that's the way that chemists use to measure the acidity of a solution. In order to derive that, I want to show that when you have pure water in a beaker, it is what I called a non-electrolyte. There aren't enough ions to conduct electricity, but water does split back into H plus and OH a little bit. This is an equilibrium reaction, and they call it the auto-ionization or self-ionization of water. Water does this on its own without you having to do anything to make it happen. Because this is an equilibrium, you can write an equilibrium constant for it. The Kw, the W is for water, of course, equals the product of those two ions, and the liquid water does not go in the denominator. Chemists have measured this number to two significant figures. At room temperature, it's actually 1.02 something, but most people just use 1 times 10 to the minus 14. This is the only number that you actually have to remember in Chem 132, the only one. This number is just as important this semester as Avogadro's number was last semester. 6.02 times 10 to the 23rd is, even if you don't see that number in a problem, it's still, every time you use moles, that number is behind it. In this, you don't always see 1 times 10 to the minus 14 in problems, but every time you use pH, this is the number that's behind it. And we're going to use it throughout the whole semester. If you boil water, the Kw changes by about 10 times. And if you bring it down to almost freezing, it changes by 10 times in the other direction. But at room temperature and usually at body temperature, which is very close, 25 degrees and 37 degrees C, they assume that this is the number and this is the basis of the pH scale. The first question is, what is the relationship between the concentration of H plus and OH minus in pure water? Since the water is splitting apart 1-to-1 into H plus and OH, you're actually going to get equal amounts of H plus and OH, and so in pure water the two ions are equal. If you do not have pure water, let's suppose you put in an acid so that the H plus goes up. That means the OH has to go down because the number 1 times 10 to the minus 14 has to stay constant. This is the same kind of a relationship that you saw between pressure and volume last semester. Is called Boyle's law. This is a hyperbola where x times y equals a constant. The pressure times volume equals a constant because if you increase the pressure, the volume goes down and vice versa, and it's a hyperbolic relationship. Some people think, well, why can't you just then express the acidity of a solution as the concentration of H plus, keep it simple? But that is actually not simple. It's more difficult. What chemists do is they express the concentration of or acidity as a log scale. And the actual formula that calculates pH is that pH equals the base 10 logarithm of the concentration of H plus. You have a key on your calculator, and most of the time it says log. So if you take the log of a concentration, you get the pH. First of all, why do they call it pH? Anytime you take minus the base 10 log of any variable in science, you can replace it with a lowercase p. There's also a POH minus the log of OH. There's a pKa minus the log of Ka. In biochem, we have one called Pi. It's minus the base 10 log of the ionization constant for a protein. This is a very common thing to do in math. I want to show you a little bit about what logarithms are, not because you really have to know specifically. If you can remember when to hit the log key on your calculator for a particular problem, you'll be in good shape. But I want to show you a little bit more than that because it helps with a lot of the properties. What is a logarithm to begin with? The definition of a logarithm is the number that you have to raise 10 to as a power to get the number you're talking about. The number itself is what's called the anti-log, and there is no anti-key on a calculator, so if you want to get an anti-log, you usually have to hit second log or inverse log. And if you look at your calculator key, wherever the log is, if you hit second log, there's usually 10 to the x or something like that above it, because the calculator knows that that is an anti-log. The logarithm, therefore, is an exponent. And because pH is a logarithm, pH acts more like an exponent than it does the number. Let's do a very simple one. And if you've had college algebra, this is like kindergarten, but I want to do it anyway to give you the idea of how this works. So, what would be the logarithm of 100? The log of 100 is whatever you have to raise 10 to in order to get 100. So the log base 10 of 100 would be 2. What is the anti-log of 2? That would equal 10 squared, or 100. These are inverse functions. And so that's how logarithms actually work. Why do chemists want to use a log scale? This is my representation of it. Let's say that you wanted to measure a biological property or a chemical reaction rate versus the concentration of H plus on the x-axis. The thing you're measuring it against could be all kinds of different things, the rate of a reaction or an enzyme activity. They have different activities depending on the concentration of H plus. It doesn't really matter what the y-axis is. The H plus axis I showed so that I showed where 1 molar is. And that's the same as 10 to the 0, because anything to the 0 is 1. If you want to go to 0.1 or 10 to the minus 1, you have to go all the way down to 1/10 the distance. If you want to go to 10 to the minus 2 or 0.01, you have to go down again. The thing is, almost all the H pluses that we look at in this class are crammed into that little tiny red line right next to the y-axis. It's hard to see. What you do when you want to make a log scale like pH is, instead of putting the number on the x-axis, you put the exponent or the log. So 10 to the 0 on a pH scale would be the number 0. 10 to the minus 1 would be 1, because remember, it's minus a negative. It's minus the base 10 log. 10 to the minus 2 would be 2. So all of those little numbers that are crammed next to the y-axis in the top graph get spread out in the log graph so you can see them. So log graphs spread out little tiny numbers. The other thing they do is they cram together big numbers so that they fit on the page. Let's say that I remember this number, I don't know why. 93 million is the number of miles from Earth to Sun. I don't know why I remember that, but it's 9.3 times 10 to the 7th. If you were trying to put 93 million on the top graph, the 93 million would probably be on the Sun, because this is only 1, what we can see here. The thing is, if you put that on a log graph, you would only use the 7, 10 to the 7th. So you would be able to cram those huge numbers all onto one axis. The other thing that a log scale a lot of times does is the graph for an ordinary graph would be a curve. Computers don't really like curves. They like lines to work with. And so a lot of times, depending on the function, if you take the log of a function and graph it, it will turn a curve into a straight line. And this is what's called linear regression in math. So there's several different reasons why chemists use a log scale, and pH is one of them that it really helps for. There's all kinds of log scales in science. I showed a couple of examples here. The decibel scale is actually a log scale, so that if you have a sound that's 20 decibels and another one that's 40, it's not twice as loud. I believe that means that it's 10 squared as loud. You don't multiply, you use the power. The Richter scale is another one. If you have an earthquake that is a 5 compared to an earthquake that's a 7, it's not just somehow 2 worse, it's 10 squared or 100 times worse, the one with the 7, because it's a log scale. This happens a lot in science. If you wanted to calculate the concentration of H plus and OH in pure water, you could do it because they're equal. If you started with the Kw and you put an x in for each of them, H plus and OH, you would get x squared equals 1 times 10 to the minus 14. And then you take the square root. You can do this on a calculator, but you can also do it in your head. And if you're going to take the MCAT or the PCAT, this is a good idea to know some of these properties. So how'd you do it in your head? Do you remember that taking the square root is the same as raising to the 1/2 power? So the square root of 10 to the minus 14 is the same as raising it to the 1/2. When you have the exponents like this, you're supposed to multiply them. So this would actually equal 10 to the minus 7. You'd get the same answer if you did it on your calculator, 1 times 10 to the minus 7, but you can do it in your head. Since you now know the concentrations in pure water, you can get the pH of pure water by taking minus the base 10 log of H plus. And you can also get a log in your head if it's 1 times something. The log is just the exponent of 10. So the log of 10 to the minus 7 would be minus 7. The reason why they make it minus the log is they want the pHs to most of the time come out positive. So this is the reason why the pH of pure water is 7. There's also a pOH. If you take minus the log of OH, it's equal to the H plus in pure water, so the pOH is also 7. When you have a solution where the pH and the pOH are both 7 and they both have a concentration of 1 times 10 to the minus 7 molar, that is what's called neutral. The solution doesn't act like either an acid or a base. I'm going to show you, this is our first real conversion formula where you can calculate pH, that anytime you add the pH plus the pOH of a solution, they have to add up to 14. If you take 7 plus 7, of course, they add up to 14, but it doesn't matter what they are. They will always add up to 14. So why? If you look at what you're doing, you're actually taking 10 to the minus 7 times 10 to the minus 7. How do you get the exponent if you have the same base with different exponents? You're supposed to add them, right? So what you're really doing is adding the pH and the pOH because they act like exponents. They have to come out to 14. Let's say you change the H plus to -3. Well, that's up, so the OH would have to go down to 10 to the minus 11 because it still has to add up to 14. This then gives rise to another conversion formula. Because of the fact that H plus times OH equals the constant, 1 times 10 to the minus 14, you could divide both sides by H plus. Then you get a formula that says OH equals the constant over H plus. But you could just as easily have divided by OH, and then you would get that H plus equals the concentration divided by OH. You have to get to the point where you can do these conversions absolutely automatically with a calculator, because we're going to use them in almost every class from now on. pH is very important in Chem 132. I kind of like to try to remember them in words rather than in formulas, because the words make more sense to me. We already know the one where if you're taking pH and POH, if you know one, you just take 14 minus and you get the other. I say the one for H plus and OH, that if you know one, you take 1 times 10 to the minus 14 over one of them gives you the other. I like that better. Now let's suppose, though, that you add acid to a solution. What happens to the pH? If you start with a neutral solution and you add enough H plus so that the concentration goes up to 3.7 times 10 to the minus 3, that is up, because 10 to the minus 3 is a bigger number than 10 to the minus 7. What happens to the pH? You can do this on a calculator. When the H plus goes up, if you take minus the log of 3.7 times 10 to the minus 3, on your calculator you'll get 2.43, which means that when the H plus goes up, the pH goes down. And now we can all cry together, because I know that you do not want this. You want it so that when H plus goes up, pH goes up. Why can't they go in the same direction? Chemists like to confuse me. Well, the truth is, it's just a stupid math formula. So it's actually math people that are trying to confuse you, not chemists. So let's put the blame where it's due. I'm just kidding. This is how pH works. So let's suppose that you dissolve an acid in water and you have the Kw equation. If you increase H plus, what has to happen to OH? It will have to go down, and so will the pH. This is a drag because pH goes in the same direction as OH. It's just the way it works. You have to get used to it. If you dissolve a base in water, which of the two ions is going to go up? If you dissolve a base in water, the OH is going to go up, which means the H plus has to go down. And that also means that the pH goes up. This is where the rules come from about what pH acidic and basic solutions have. Because more acidic means the pH goes down, that's the reason why acidic solutions have a pH below 7. And that's also the reason why basic solutions have a pH above 7. And I want you to know that the words basic and alkaline in pH chemistry and acid-base chemistry, they're synonyms. If you're using an alkaline battery, for example, you're using a battery that's based on half reactions that have OH or bases in them. I don't want you to just memorize these formulas and conversions and things. I want you to have an idea of what different acids and bases are actually like. So I have a picture here of a pH scale, and I chose the stuff I wanted to have on it. If you look at where neutral is, right in the middle, you can see that acidic is below and basic is above. This is kind of what's called the physiological pH range. Usually they use 1 to 13. These are pHs where in that range, if you pour the solution on your partner's head, their hair will not come sizzling down their face as you watch. If you get out of that range, it's probably going to be pretty corrosive. So I want to look, first of all, at what kinds of things are acids. If you look, I think of acids, when I think of that, I think of either lemon juice or vinegar. Those are both sour. Acids are sour. And if you get either one of those on an open cut, you're going to be very sorry because it hurts. That means that they are also corrosive. The other thing is that they will change indicators to a certain color. If you did an experiment with phenolphthalein as an indicator, a titration, you know that that particular dye is colorless in an acid and it's pinkish or magenta in a base, and so it turns indicators of color. Do you see that right above it is soda pop? That means Pepsi has almost the same pH as lemon juice. It's part of the flavor. Now, if you want to look at your stomach acid is really low, because in order to digest food, you need a very acidic pH. The enzyme pepsin, which is what dissolves proteins in your stomach, will not even work above pH 2.5 or so. So it's got to be very acidic to digest food. Now let's look at the basic range. I have the classic base as ammonia. We're going to talk about why NH3 is a weak base next class. The thing is, that is a very classic base. The next one down says mom. What the heck is mom? Is your mom is basic? What does that mean? I don't know. But anyway, that stands for milk of magnesia. That compound is magnesium hydroxide, MgOH2. You can buy it in the drugstore as a thick white solution that's an antacid, and they call it also mother's little helper, because if you get kids, you will find out why you need an antacid. So you can drink mom and it will soak up the excess acid in your stomach and take away your indigestion. It's also a laxative. That's another reason probably why they call it mother's little helper. The thing is, the magnesium ion does not get absorbed from your intestine as well as others. And so it kind of sits in there. And when you get a salt in the intestine, it draws water by osmosis from the external tissues. And when you get the intestinal contents plus water, you basically get whoopee. That's a laxative, see? So this is the reason why, and it's magnesium hydroxide has OH in it, and it is a little bit soluble in water, not very much, so it makes a basic solution. Now, your blood is about pH 7.4, so it's slightly basic. I want to introduce a word that we're going to use later in the class. If your blood goes down to pH 6.4 instead of 7.4, is that good? That means you are going to be dead in the water, because that is a state that's called acidosis. It's too low pH. What causes that? Why don't you die of acidosis if you just drink a 2-liter Pepsi? The reason is that your blood is what's called a buffer. That's what I have a definition of at the bottom of this page. Buffers have things in them that resist the pH from changing, even if you dump in an acid or a base. Your blood is an excellent buffer because that is what you need to maintain pH in order to keep your system working right. The only thing I know of that will make your blood go down that low is some kind of a pathological process, and the classic one is uncontrolled diabetes. If you have a diabetic that does not get their insulin, glucose cannot get from the blood into the cell, and the cell thinks it's starving, so it shifts to using what are called, or it's fats, and they burn fat. It produces what's called ketone bodies. Those are a poorer energy source, but you can use them for that. But the thing about ketone bodies is they're acids. And so you're dumping all this acid into your blood, and if you don't get your insulin, eventually the pH of your blood's going to go too low, and that's part of the mechanism of coma and death in an uncontrolled diabetic. And of course, you can understand that it's no better if your blood goes up to 8.4. That's called alkalosis, and you can die of that also. So the thing is, your blood needs to be a buffer in order to keep the pH constant. This is where I want to say I can summarize all of biology in one word. I'm a biochemist. My word that summarizes all of biology in one word is the word homeostasis. That's what biology is all about. Anytime you have a system that's at equilibrium, it could be an organism, an ecological system, or anything else, a predator-prey relationship. If you change one of them, the other one has to adapt so that they go back to equilibrium. That's what biology is all about. And pH is one of the very critical ones. Seawater is a buffer, blood is a buffer, the inside of your cells is a buffer. Buffers are for the purpose of maintaining homeostasis. And so this is where I wanted to mention that we're going to do 2 whole lectures on buffers later in the course. I apologize, that was a very long slide, but that's okay. I wanted to say all those things. What I want to do, though, before the end of this class is make sure that everybody knows how to calculate all of these pHs. And what I'm going to do is, let's say this, I ask you a problem like this. If H plus equals this concentration, what is the pH? The way I ask this, both on the first exam and in homework, is what it looks like on the next slide. I give you all 4 of the possible columns: concentration of H plus, OH, pH, and POH. I give you one of them, and I want you to calculate the other 3. And I want you to be able to do that in any combination possible. So I gave you the H plus this time. How do we get from that the pH? Since pH is minus the log, we're going to take minus the log of that number, and it comes out 10.63, which is a basic solution. What is the POH? Everybody likes this one, because all you have to do to get that one is 14 minus. So pH and POH have to add up to 14. How are you going to get OH? I've only shown you one way so far, and that's by using the kW of water, so that 1 times 10 to the minus 14 divided by one of them gives you the other. That is the correct answer, but I challenge you that if you do this problem and you end up with something like 10 to the minus 24 or 5 instead, or 26, what you did was you forgot to put the denominator in parentheses. You have to get both the exponent and the number in front, the mantissa, correct. Otherwise, it's wrong. So please remember, always put denominators in parentheses, and if you're not using the EE key, always put scientific notation in parentheses also. So here I completed that line, and we got all 4 of those. The only conversion that I haven't really shown you is to go backwards. Let's suppose that you are given that the pH is 6.11. How do you go backwards and get H plus? So we got to get the other 3 columns here when the pH is 6.11. I want to do it by starting with the pH formula. pH equals minus the log, and so you can switch the negative over to the other side, and then I put the log on the left, so the H plus is the variable. Now, how do you get rid of a log? You'd like to throw it in the fireplace and burn it up, but of course that doesn't work in math. You might want to divide by log, but guess what? That doesn't mean anything. If you want to get rid of a function, you have to take the inverse function. I mean, if you want to get rid of plus 2, you take minus 2 because that's the inverse. So what you're going to do to get rid of that log is take whatever the inverse log is. When you take the inverse log, you have to do the same thing on both sides. The inverse log of a log is going to make the log cancel out. If you do this on your calculator, then you'll just have h plus left on the left. And in order to take the inverse log of negative pH, you have to just put inverse log in your calculator. And the same thing also works for OH. If you want to get the OH from the POH, you take the inverse log of negative POH. The thing is, you absolutely have got to remember in this formula to put the negative in front of the pH. If you take the inverse log of a positive pH, you're going to get molarities that are not even possible. You must remember that it's the inverse log of negative pH. And I showed you before that the inverse log is actually 10 raised to the power. So when you hit the inverse log on your calculator, you're going to get 10 raised to the power. So taking the inverse log is actually the same as getting 10 raised to the negative pH power. And it's the same for POH. So that's another way to get it. In order to get the H plus, then from the pH, I took the inverse log of negative 6.11, and that gives me the concentration of H plus. Then how do I get POH? You just take 14 minus, and that will give you the POH. Now, we now have two different ways to get OH. One way to get it is by taking 1 times 10 to the minus 14 divided by H plus gives you OH. But we've got a second way now. You can take the inverse log of negative POH, and that should give you the same answer. You have to realize at this point that you might not get exactly the same numbers as I do, because in rounding, exponents cause even more round-off error than multiplying numbers. So if you get 1.5 or something, you don't want to lose any sleep over it as long as the exponent is correct and it's close to the number I get. You'll get a feel for that when it's right and when it's not. I had a hard time actually finding a pH where you get the exact same answer within keeping a reasonable number of significant figures. So if you're off a little bit in the H plus or OH, it'll still be correct. So we got all four of the ones for that row where the pH is 6.11, and there they are. Next thing I want to ask is, are there pH 0 or even negative pHs? And the answer is yes. It's just a stupid formula. In math, it's possible. So let me show you. If the pH is 0, that means to get H plus, you're supposed to take the inverse log of 0, and 10 to the 0 power is 1. So a pH of 0 corresponds to 1 molar acid. A pH of 14, or a POH of 0, corresponds to 1 molar base. And here's the summary. The thing is, there are negative pHs also, but what happens is, if you have a pH of -1, that's actually 10 molar. By the time you get to that much acid, people don't use usually pH anymore. They give you the molarity. So you very rarely see pHs that are negatives below 0, but they do exist. It's just a formula, but it's better to use molarity when it's that low. Now these formulas, like I said, you definitely want to be able to know very well, but you don't have to memorize the formulas. What I want you to know is how to do each one of the conversions on your calculator by keystrokes. In other words, what key do I hit to go from H plus to pH or something? I summarized the formulas here that pH and pOH mean minus the log because the lowercase p is minus the log. The reverse formulas are the inverse log of negative pH or pOH. At the bottom here, we have the formulas that say 1 times 10 to the minus 14 divided by one of them gives you the other, if you're talking about H plus and OH. And the pH and pOH always add up to 14. I don't like these formulas as much as I do using words. So let me show you on the next page how you can remember this by words rather than formulas. You might like this better. If you're going from H plus to pH, in other words, molarity to a number, just an ordinary number, or the same for OH, the function you want to use is minus the log, because a lowercase p means minus the log. If you're going in the reverse direction, you're going to go from a number like pH to a molarity, H plus. The function is the inverse log of negative. If you can remember those two and which direction they're for, that pretty much will cover you. Because most people know the last two, that 1 times 10 to the minus 14 divided by one of them gives you the other for H plus and OH. And most people know that if you subtract 1, 14 minus, you get the other. So if you learn the formulas this way, some people like these better. This one that's in yellow here is, you could use it for practice. You can use your calculator and see if you can go from one to the other in any of these combinations. The truth is I have about 8 lines of these on homework 2. So I give you one of them and I ask you for the others. If you can get those ones from homework 2 right, and of course the answers are there and they're worked out online, you can get, you figure you can do pretty good if you know how to do all of these. Please let me remind you, since this is our second class and I'm going to keep reminding you of this, the worked out homework is online. You can look at the homework step by step worked out if you go to the modules and you look under homework. Worked out homework is there, and you can choose the homework that you're talking about, and it'll show you not only the answers, which are in the back of the homework assignments, just like a textbook, but also the worked out homework is also there, so you can see it stepwise. So now you should be able to do homework 2, and next time we're going to do more detail on calculating the actual pHs of acids and bases.